remind you what we need to prove, right? And then sketch, give some schedule how to prove that inequality. So we need to prove that f of a minus f of b norm less than or equal to the norm of f of a minus b, where this guy is unitarily invariant norm, right? And INT just greater than or equal to 0. So let's say the idea of the proof. First, we prove this for a minus b greater than or equal to 0, right? And even for this case, we need to prove for the case where function f is just f of st, which is, as I remember, st over s plus t. You remember that? And then, since the function f is operator monotone function, f has the following representation: a plus bt plus integral from 0 to infinity st d. I mean, I can write in short just sf of st dt, right? Yeah, not dt, but let's say ds. Ds, something like that. Makes sense? Here is t. Here should be, I think, here should not be, it should be fst. And let's say, I think here we don't have s because we include s in here.
Yeah.
Okay, so that is our strategy. And then we prove for this, and then we generalize the case to this. So this is the first thing. And then we move to general case, right? To general case, and then for general case, we consider we can rewrite this a minus b equal to z plus minus z minus, right? Where z plus and z minus are positive and negative parts of a minus b. And then for this case, we will use the first case. We use the first case, and we separate. It's very standard technique for that. So let me go back to the case of a minus b greater than or equal to 0. We use following identity: b plus 1 negative 1 minus b plus c plus 1 to negative 1 equal to, I think that is b plus 1 to negative 1 c, b plus 1 p plus c plus 1, right? To negative 1. That is you said Hilbert identity? Yeah, it's a Hilbert identity. And then we use the fact that actually this difference is equal to f of s b plus c minus f of s b. Right? Actually, that's the thing. And then we rewrite this product in the form, something like, we change that. That is right from b plus 1 to negative 1/2, c b plus 1 to negative 1/2, and then everything we apply this to the function h1, where h1 t over s is equal to f of st, something like that. And then you remember this guy is contraction, right? Contractions mean the norm is less than equal to 1. This guy is contraction, so when we apply singular value to all these operators, so we can remove the contraction. Right? Do you remember that idea? So that is very important. So just try to remind you. And then since we have h1 in here, we move to h1 singular value of c, and since h1 is increasing for increasing functions and singular values, we have this identity that is SI H1C. So H1C, from here we go back to the case f of S, absolute of A minus B. So that's what we did last time, right? All right, so now let's consider a general case.
Which means A is no longer greater or equal than B of A. Or not related. But general case, it means
Yeah, general case just A and B.
no connection.
Yeah, no connection, just positive semi-definite matrices. So for him, you know, positive semi-definite matrices, but you know Hermitian matrices. You know, but he didn't know.
We have taught it in quantum mechanics.
So yeah, they do that in quantum mechanics sometimes because between matrices, when you involve distance, right? You probably you did dot product. We do dot product in my course, right? And then you consider some AX and X. So for any matrix and for any X, you consider you apply matrix to the X, right? You have some vector. Then you take dot product of this vector and this vector. If this guy is greater than or equal to 0, we say A is positive semi-definite. Yeah, it's just one step from intangible. Makes sense? All right, so in general case, I will write A minus B plus equal to Z plus A minus B minus equal to Z, negative, right? I mean, we just say, and then A minus B in this case equal to Z plus minus Z minus an absolute of A minus B equal to Z plus Z minus, where this is called negative part of this matrix, this is called positive part of this matrix. So I hope you still remember, right?
Well, remind us, positive, negative part, you get them out of the...
Okay, let's say for Hermitian matrix, you have a spectrum decomposition, right?
Mm-hmm.
1 to n. And among these eigenvalues, you separate negative and
from
positive,
negative.
negative and positive ones.
Then you group them and you form two matrices, one with positive, one with the other with negative one.
So for example, if you group them together with lambda I pi, where lambda I is less than 0, right?
Mm-hmm.
And then here you have lambda I pi, where lambda I greater than 0. So this guy you denote by Z plus, right? Or you denote by A plus. But this guy you denote by negative A minus, because we want to keep A plus and A minus positive.
So you pull out the minus.
Yeah, we pull out minus, and then that's why we always have this decomposition. Sometimes they call this is Jordan decomposition. Okay, so you see, if you take absolute, so, and very important property is that A plus times A minus equal to 0. This is obvious.
It's clear because of
Yeah, from here, from
when
this.
we're talking on projectors, part of them go here,
Yes,
part
yes.
go there, and they're mutual.
And then when you multiply them, you see all you take product of any project orthogonal projection in here and any orthogonal projection in here. You get 0.
They
Because
don't
they are
coincide because
they are orthogonal. Make sense? So that's why you have this. And not only that, if you apply any function to this, right? Not only this, if you apply function f of A plus, and then you multiply with f of A negative, you also get 0.
any function.
I mean, yes, any function which are defined at eigenvalues of this. I mean, again, you use this decomposition. For example, what is f of A plus, right? F of A plus is sum of f of lambda I pi, right? Where lambda I greater than 0.
Oh, you mean because of
Yes.
projectors stay the
Yeah,
same?
because projectors stay the same, right? And so when you multiply them, you get f of lambda I in here and pi, or let's say bj and j, so that lambda j less than 0. You see, each time when you multiply this guy with this guy, you give 0, you have 0.
No matter what f
Yeah.
of lambda is.
So this is very important in the rest of the proof. Agreed? All right, so once we do that, we see that actually from this identity, I have A equal to Z plus B minus Z negative, right? And B is equal to Z negative plus A minus Z plus. So what does it mean? That means A less than or equal to Z plus B, right? Because Z negative is positive. Make sense? And here we have B less than or equal to Z negative plus A, because this guy is positive. We will use this inequality once we involve operator monotone function. From here we might have f of A less than or equal to f of Z plus B, right? And then here we have f of B less than or equal to Z, f of Z negative plus A. So that's what we need for the future. All right. So let's rewrite that inequality, right? For this case. So what do we have? The left-hand side, if the left-hand side, I still can use, let's say, but the right-hand side, let's say, what is f of A minus f of B, right? Let's say if I involve I'm trying to use the way, not in the proof of Ando. Maybe we use this. This is equal to f of A minus f of Z plus f of Z minus f of B, where Z is A minus B, something like that. And maybe we have to break this into the norm of f of A minus f of B equal to the norm of f of A minus f of Z. Let's say less than or equal to, right?
Triangle inequality.
Triangle inequality, right? F of B. Agree? This works for any Z, right? So now let's pick, for example, Z is equal to this, one of them. And then let's pick Z equal to this for another one. This happens for any Z. So we might have the following one. This is equal to norm of f of A minus f of Z plus B. Right? And let's say, have to be very careful. F of Z plus B. No, but I don't have that. Probably I need to, because A minus that is equal to Z negative. No. I try to get one term is equal to f of Z minus and another term equal to f of Z plus. And so when you compile them, you get f of Z minus plus f of Z plus. That is f of Z plus Z minus, right? And that is f of absolute of A minus B. That is my proposal.
Yeah.
That's my proposal. But again, I think maybe it will not go too.
No, that's right, that will, because if you, I mean, you can do it for Z plus B and Z minus plus A. And if you do it twice, then add.
Let's see.
So Z plus B.
Yeah, actually, I still can do that, but I need more work. Let's say that. I need more work in this. That is not the proof in the paper.
But this makes sense. I mean.
Yeah, that makes sense. But again, right? Let me tell you another one. The thing is, if we have trace, everything is good. Because I remember my paper with the trace. With the trace, we can we just remove this and write a trace, so we don't have any problem when you take sum or difference. But here the norm, so probably we need to go back to the proof, and we need to use the K key fan norm. Let's use the K, the key fan norm, okay? So I don't try to make me smart. Maybe next time I will show you the proof of my inequalities with the trace, and you see actually there's some relationship with this. But let's do that. So in general, I have the following inequality. Okay, let me see. Yes, I think it's done with this. So I have f of A minus f of B less than or equal to f of B plus Z plus minus f of B. That's what we have in here, right? Because of this. So because f of A less than or equal to this guy, so when you just this is clear. And then from here, let's say f of A minus f of B, and you take the positive part, right? And you apply the K key fan norm. This is less than or equal to f of B plus Z plus minus f of B, K key fan norm. Yeah, this is one, some kind of lemma, like if you have, let's say, if you have some A less than or equal to B, right? Then A equal to B. And since you can say B is greater than or equal to 0. From here, A plus less than or equal to B, let's say that. And that makes sense, because if A is a Hermitian, you can represent A as A plus minus A minus, right? But since A plus and A minus, they have different direction in here. So probably this part should be less than or equal to this guy. I mean, that is reasonable, right? I mean, we don't need a strict proof, but you imagine and believe that. So from that observation, you can see you take plus, you take positive parts of this guy, right? And then you take, what is K key fan norm? That's sum of the first K eigenvalues, right? Or singular values, but in this case, positive, so eigenvalues. So you make this, and then you sum them up, you get this guy equal to less than or equal to this guy. The thing is, we don't need this is positive, because this matrix is already positive. This matrix is already positive, because B is greater than B, right? B plus Z plus greater than B, and since F is operator monotone, so that's why this is already positive, semi-definite matrix. But so we don't have plus in here, but this we need plus. Agree? Okay, next. So what's the next? We do the same thing for that, and we see that actually f of B plus Z plus minus f of B. K key fan norm less than or equal to f of Z plus K key fan norm. Why do we have that? We have this inequality from the previous case, because this guy is greater than this guy, right? So if we apply the case when A minus B greater than or equal to 0, in this case, you see, if this is A, this is B, right? So this is nothing but A minus B, right? So this inequality follows from the previous case. Right? Make sense? So for these matrices, okay, we have this inequality. So that means we say the key fan norm, if we have this inequality for any K, right? So we have norm inequalities, right? I mean, K key fan norm, that is very powerful. From here we have S of f of A minus f of B, and then plus. See? From here and from here we just from this inequality and this inequality, we have the K norm of this guy less than or equal to this guy, right? You see? You see, this less than to this less than to this. So that means the first guy is less than to the third guy, right?
Transitivity.
Yeah, transitivity. And then this is less than or equal to singular values of, with majorization, as of f of a minus b plus, or just, that is nothing but z plus. Okay, so then now we interchange the role of A and B. We interchange the role of A and B. So we will see, we make this, we have, let's interchange the role of A and B. So we can see actually S of what? F of A of B, right? Let's say that F of B minus F of A plus, right? This is with majorized by S of, say, F of B minus A plus. But if you change that, so that means just you switch from positive part to negative part, right? So what is this? That is F of negative A minus B.
Oh, I mean from A minus B to
Yes,
B minus A.
yes. You just change, change from negative part to positive part. Make sense? So that means from here we have, I will erase this. From here we have S of A, F of A minus F of B, and then negative, with majorized by S of F of A minus B, negative. And now we compile this inequality and this inequality, right? This guy with this guy. Compile them together. So we have the following one. S of F of A minus F of B plus S of, no, might we have that or not? Because the important thing is, because as I mentioned in here, right, if you have positive and negative part, when you apply this and this, that they still orthogonal. Make sense? So that's why we can compile together. Usually, you see, I will tell you later about that. F of A minus F of B, negative, with majorized by S of F of A minus B plus S of F of A minus B minus. We can sum inequalities for majorization if and only if the product of this guy and this guy is 0, means they are orthogonal. Otherwise, in general, we don't have this. A majorized by B and C with majorized by D. From here, we don't have A plus C with majorized by B plus D. We don't have that in general. But in case this guy and this guy are orthogonal, means the product is 0, right? This guy and this guy are orthogonal, means the product is 0, so we can make that. And then from here, you compile all them together, you get, S of F of A minus F of B, which was divided by S of F of A minus B. Because of this, because A minus B is equal to Z plus Z minus this. And that is the whole idea of the proof. Make sense?
A little bit.
A little bit.
Yeah.
Yes, a little bit. That's fine.
Yeah, if you see it in writing after that,
Hmm?
you can follow the main steps here.
Yeah, the main step in here. So first, we need to see the idea, right? The idea of the proof and how everything goes. And other things here, I think this proof works for Fs, right? I didn't say anything about integral. I didn't say anything. But for integral, for this part, this linear part does not affect, right? Because that's just linear. For integral, you can apply operators or something like that for integral, and you consider